Hello everyone. We're going to go through another example with multiple recurrences here. This one is going to be different than the previous ones because this is a divide and conquer type problem. In this problem, we are taking the variable on the right-hand side and dividing it by things. We have t of n over 2 plus 2t of n over 4 plus cn. So for this problem, we have a recursive calls that look like n over something. That makes the analysis slightly different. But just for somewhat consistency, let's begin by trying to bound it below like we have the previous problems. Bound below. To bound below, we need to identify which of the terms is smaller. The t of n minus 4, and by t of n minus 4 I mean t of n over 4, is the smaller term. So this is smaller. So when bounding below, we have t of n greater than or equal to. Replace the t of n over 2 with a t of n over 4. Plus 2 t of n over 4 plus cn. And I'm actually not going to drop the cn in this problem. So we have t of n greater than or equal to 3 t of n over 4 plus cn. And now we need to analyze this algorithm and see what happens. So we need to plug n over 4 into that equation, which maybe I designate with a black bar. So I'm going to plug n over 4 into the black barred equation. Doing so, I get t of n over 4 on the left-hand side is greater than or equal to 3. T of n over 4 is n over 16 plus c n over 4. Then I substitute that into the black barred equation and have... let's write that more to the left. T of n greater than or equal to 3 times my right-hand side there, 3t of n over 16 plus cn over 4. Plus I still have that cn out there at the end. Let's distribute the 3, and we get t of n greater than or equal to 9 t of n over 16 plus distribute the 3 and we get 3cn over 4 plus cn. Now, let's make another substitution. So let's plug n over 16 into the black barred equation. Into black bar. Making that substitution, we have t of n over 16 on the left-hand side is greater than or equal to 3. T of n over 16 over 4, which is n over 64, plus cn over 16. We then substitute that into the blue equation and have t of n is greater than or equal to 9 times, make the substitution, we have 3t of n over 64 plus cn over 16 plus all those additional terms we had from the original problem. So 3 cn over 4 plus cn. Distribute the 9 and see what happens. We have t of n greater than or equal to 27, t of n over 64 plus 9cn over 16 plus 3cn over 4 plus cn. Now we need to identify a pattern. This pattern is not necessarily obvious, but let's try. The first term here, the 27 and the 9 and the 3, hey, those are powers of 3. So that looks like 3 to the k. The t of n over stuff looks like t of n over 64, n over 16, and n over 4. That's n over powers of 4. And the remaining terms look like a summation. The sum from I equals 0 to k minus 1 of the things in the numerator, 9cn, 3cn, 1cn. That looks like 3 to the I times c times n. Over the denominator, 16, 4, and 1 looks like powers of 4, 4 to the I. So let's use all of that. So we have that for any value of k. That t of n is greater than or equal to 3 to the k times t of n over 4 to the k plus the sum from I equals 0 to k minus 1 of 3 to the I times c times n all over 4 to the I. We need to identify when does the recurrence relation terminate, so it stops when the thing inside of t, which in this case is n over 4 to the k, is equal to the base case. What was our base case? Well, let's scroll up and find it. Our base case was t of 1 is equal to c. So we set n over 4 to the k equal to 1. Skipping some algebra, we solve that for k and get k equals log base 4 of n. Let us substitute that into our generic expression for k. So we have t of n greater than or equal to 3 to the log base 4 of n times t of 1. I know it's t of 1 because I chose n over 4 to the k to equal 1, plus the sum from I equals 0 to k minus 1 of 3 to the I times c times n all over 4 to the I. Now I need to analyze that summation. So let's try and do that in place here, actually, this time. So we have t of n greater than or equal to. I'm going to do a couple of things at once here. 3 to the log base 4 of n, I can rewrite as n to the log base 4 of 3. T of 1 I know is equal to c, because that's my base case. Plus, I can factor a cn out of that summation because they have nothing to do with I. Then I have the sum from I equals 0 to k minus 1 of 3 over 4 all raised to the I. And maybe we identify that that summation is a geometric summation, and we know that it is in theta of 1. So I can easily bound it below in the following way. I still have my n to the log base 4 of 3 times c plus cn. I'm going to bound that summation below by replacing it with the number 1. That summation is equal to 1 plus 3/4 plus 9/16 and so on. If I drop all of the extra terms except for the first, the number 1, then I definitely make it smaller. Now, which term is larger? N to the log base 4 of 3 or n? It's going to be n because log base 4 of 3 is less than 1. So, t of n is in big omega of n. That seems all well and good. Now hopefully we can show it's in big O of n. Let's try and do that. So we still need to bound this above. To bound it above, we're going to take the original equation, t of n equals t of n over 2 plus 2t of n over 4 plus cn. So let's write it down again. Equals t of n over 2 plus 2 t of n over 4 plus cn. We're going to bound it below by replacing the smaller term, t of n over 4, with the larger term. T of n is less than or equal to, now, t of n over 2 plus 2 t of n over 2 plus cn. And now, let's plug in, or combine all of our like terms, and we have t of n less than or equal to 3 t of n over 2 plus cn. Now we need to perform our substitutions. So we need to plug n over 2 into, let's give a designation for this equation. I'm going to designate it with a red bar. So I'm going to plug n over 2 into the red barred equation. Making that substitution, we have t of n over 2 is less than or equal to 3 t of n over 2, which is n over 4, plus cn over 2. Let's substitute that back into the original. So that gives us t of n less than or equal to 3 times 3t of n over 4 plus 3cn over... Sorry, just skipping ahead. Plus cn over 2 plus, I still have a Cn in the original equation. Let's distribute the 3, the step I was trying to do already. This is less than or equal to 9 t of n over 4 plus 3cn over 2 plus cn. Now, let us do another substitution. So let's plug n over 4 into the red barred equation. Making that substitution, we have t of n over 4 is less than or equal to 3 t of n over 4 over 2, which is n over 8, plus cn over 4. So we plug that back into the blue equation above there, and we get t of n less than or equal to 9 times make the substitution. We replace it with 3 t of n over 8 plus cn over 4 plus 3cn over 2 plus cn. Distribute the 9, and we get t of n less than or equal to 27 t of n over 8 plus 9cn over 4 plus 3cn over 2 plus cn. I don't know how that happened. 3cn. Now we must identify a pattern. I'm going to go through this a little bit faster than before because we've seen some of this before. The coefficients out front is the exact same pattern. That's 3 to the k. The stuff inside of t looks like n over 8, n over 4, and n over 2. So that looks like t of n over 2 to the k. And then for the last 3 terms, we have a summation. We can write that as before, the sum from I equals 0 to k minus 1. The top looks like 3 to the I times c times n all over 2 to the I. Let's use all of that in our final way of bringing the substitution together. So for any value of k, t of n is less than or equal to 3 to the k, t of n over 2 to the k, plus the summation from I equals 0 to k minus 1 of 3 to the I, 3 to the I times cn all over 2 to the I. We then again must identify when does this stop. So this stops when the inside, n over 2 to the k, is equal to the base case, which we might remember was 1. Let's solve that for k. That gives us k equals log base 2 of n, and then substitute it into the equation. T of n less than or equal to 3 to the log base 2 of n times t of n over 2 to the k, which is 1, plus the sum from I equals 0 to k minus 1 of 3 to the I times cn all over 2 to the I. Now let's keep doing more substitutions and simplifications. T of n less than or equal to, I can do my same trick I did last time and write this as n to the log base 2 of 3. And I know t of 1 is just c. Plus, I can, as before, factor the cn out of my summation. But then we start hitting a road bump. Our geometric stuff works really well when we have a decreasing geometric series. We do not have that in this problem, though. So let's try and analyze that summation. So t of n less than or equal to cn to the log base 2 of 3 plus cn times the summation from I equals 0 to k minus 1 of 3 over 2 to the I. Let's try and see what we can do with this summation. Maybe somewhere deep in our minds we remember a useful fact. That this summation is in theta of r to the n, where r is the thing raised to the I and n is the top bound. So this is 3 over 2 to the k minus 1. Let's use that fact. Using that fact, we have t of n less than or equal to cn to the log base 2 of 3 plus cn times theta of 3 over 2 to the k, which is log base 2 of n minus 1. This ain't looking promising, but let's keep going. T of n less than or equal to cn to the log base 2 of 3 plus theta of n times 3 halves to the log base 2 of n minus 1. This looks real bad at this point. This will happen for many of these problems. So this technique, our bounding technique, does not work well. Bounding seems to fail. We could keep going along and get something for our big O bound, but the big O bound will not match the big omega bound we found before. And this problem was awful. There is no way around it. It is bad. We are going to need to come up with a better technique for analyzing this.